Welcome to the information session. I am Professor Hongzhou Zhang. I am the Director of Teaching and Learning for postgraduate students at the School of Physics in Trinity College, Dublin. For today's session, I will start with an overview about the government postgraduate scholarship scheme. This will be followed by several research talks. I hope you enjoy today's session, but most importantly, I hope you will find a supervisor to work with to apply for the scholarship. If you have comments and questions, please ask in the comment area. We will try to address it here. You are also welcome to email the academics whose research interests you to initiate detailed talks on the research project. Well, now let's first talk about the scheme. The IRC Postgraduate Scholarship is a prestigious award. This also means it is very competitive. The successful rate from last year is about 18% for European students. This is even lower for non-EU international students, it's about 5%. However, this is not zero, so I would encourage exceptional international students to apply. The successful rate from candidates supported by our school is 40%. As you can see, this is much higher than the average. To apply, you must have a first class or upper second class grade from your undergraduate program, or if you have a master's degree, you are eligible to apply. Of course, there are some other eligibility requirements. Please refer to the core document for the details. If you are successful, your award and the PhD program will start from the 1st September 2021. Well, how to apply? Each applicant can only submit one application. Since you are the applicant, you must take responsibility to complete and submit the online application to IRC by the deadline. To complete the application, you must fill several online forms, which for your part is more or less like a CV, but you need to write a personal statement and also career plan. The most important part of the application is a research proposal. To write a competitive research proposal, you should work closely with your supervisor. Of course, your supervisor need to express their support explicitly to IRC by filling their own forms and submit it by the deadline. You also need to coordinate 2 reference letters from 2 referees who knows you. Please note the deadlines. You must submit a completed form online by 29th October. That's very close, so please act now to engage with your supervisor to work on the application, the proposal, and your statements. You need also to remind the supervisor and the referees to submit their parts by the deadline. Well, that's the key information concerning the application. Now let's start our research talks. Hello, My name is Hongzhou Zhang. The project is to enable two-dimensional neuromorphic devices. Let me first talk about the challenges this project to address. So we know for the past 40 years, electronic technologies have changed our lives. Okay, so the success of this technology we know is based on large-scale integration of semiconductor devices. So the whole success of this electronic era is based on the continuing scaling of the device to make it smaller and more powerful. However, this scaling soon will hit its limit. So this is the most pressing challenge faced by the semiconductor industry. The industry will need a technology to replace the conventional device. There have been extensive research on this. However, by far, there hasn't been a solution to this scaling problem. The overarching aim of our research is to enable the device application of nanostructured materials for this emerging computational platform. So specifically, this IRC project is to enable a new two-dimensional resistive switch which can hold its resistance state. This device is called memristors. There are actually extensive research on this memristor, but the challenge is the device variability. So that means the device performance varies from one device to the other. This is a showstopper since this issue is not compatible with large-scale integration. So the IRC project is to deal with the device variability issue. So we propose a solution based on a new fabrication technology that is called the helium-ion microscopy. My group here in Trinity have been working on this technology for 10 years. So in a helium-ion microscope, a helium-ion beam is accelerated, focused, and delivered to the specimen where the incoming ion can knock out the material atoms and leave a vacancy there. So the key advantage of this tool is its ultra-fine probe. So this means we can control the location, size, and type of the defect being introduced in the material. So there have been extensive research conducted concerning this ion-matter interaction. However, there is still a huge knowledge gap regarding the interaction that occurs at a highly confined region. The controllability in material modification will not happen without this knowledge. So this IRC project is to address this key challenge in the helium-ion research. So what we are going to make is a device like this, okay? So it's based on two-dimensional, a layer of molybdenum disulfide, electrically contacted. So these electrodes are put there by electron beam lithography, okay? And then the material is irradiated by a focused helium-ion beam. After the irradiation, we will conduct a range of characterization and electrical evaluation, okay? So this is an image of the device by the atomic scanning microscope. The device after the irradiation shows this resistive switching. So this is quite promising since we know for sure the ion irradiation can introduce the resistive switching. However, the switching mechanism is elusive. This IRC project aims to collect experimental evidence to clarify this mechanism. To understand the mechanism requires detailed knowledge of the materials and the effects introduced by the ion irradiation. This is indeed an interesting puzzle the IRC project will tackle. We will conduct advanced microscopy. For example, here is an atomic resolve image taken by the transmission electron microscopy. The microscopy results will be corroborated by optical characterization here. Okay, so these results will, of course, be linked to those from the electrical evaluation. We will then synthesize the knowledge of the ion modification and the switching mechanisms. So this project is to address two important challenges. The project is based on our 10-year achievement in the field, and we do have very interesting, promising results to validate this idea. So again, I would mention that research is experimental based. You will develop knowledge and hands-on skills in material deposition, electron beam lithography, and also a range of advanced characterizations. You will gain insight in the electronic process in 2D materials. I would like to thank you again for your attention. If you are interested, please send me an email. I will be very happy to discuss the research with you. Okay, good luck. Hope you enjoy the day.
Okay, hello everybody. I hope you're enjoying the day today. This is a presentation from my own group, which is the Computational Spintronics group. And this is a materials modeling and, if you like, a quantum physics group here in Trinity College. This is a picture of the group taken a couple of years ago. And this is, unfortunately, is the picture of the group taken now, where we, of course, go online for our meeting and so on. Hopefully we'll be back soon in class. So the interest in my group is in materials modeling, and recently materials modeling has been taken by storm by another type of technology, computational technology, which is called machine learning. Now, machine learning, you might have heard about it. It's a branch of artificial intelligence. And the main idea of machine learning is relatively simple, is the ability to navigate data. And typically what you try to do in machine learning, you try to construct algorithms that take information in a form of a vector, some type containing a number of quantities, and you try to correlate this vector with quantity that you know. So you try to establish relation between the data. Now, this is, of course, this is a huge field in computational science, and the simple concept that I gave you here, so just to try to establish relation between data, is just a small fraction of what machine learning actually does. And you might have heard about a number of applications that machine learning is having. One, for instance, is artificial intelligence and machine learning will power the self-driving car. Are using all sort of software to recognize faces and are used to interpret and manipulate language. Now, fortunately, in addition to all this pretty dystopian application of machine learning now can be applied into the solution of physical problem. And this is actually what my group has been working on for a few years now. And in particular, I mean, what we have been doing in the last few years is to try to use machine learning based on experimental data to predict known quantities. So for instance, here, this work here that I don't have any time to explain, we took the experimental information about the critical temperature of ferromagnet, and we tried to correlate the chemical composition of a material to its Curie temperature with very good success. Another way where you try to use machine learning models is to try to predict very, very accurate atomistic dynamics. So here, essentially what we do, we train models to compute forces between atoms at the level of an accuracy which is identical to the one of advanced electronic structure methods, which of course are much, much more computationally intensive. And the other aspect we've been working on is to try to solve complex many-body problem. Many-body problems are typically characterized by the fact that they require very large computational resources, and the complexity of the problem scale with the number of atoms. So for problems that contain a very large number of atoms, the methods become, the exact solution become essentially unfeasible. But machine learning, to some degree, can overcome this problem. So what is the project I'm going to offer this year going to be about? The idea is to try to combine two leading theory, one for doing materials modeling, which is density functional theory, and one is machine learning. Density functional theory, in a nutshell, is a very clever way to solve the Schrödinger equation for real materials at relatively modest computational cost. And it is based on two well-established theorems, which essentially says that the knowledge of the electron density is sufficient to determine all the property of a system. Now, this is a very advanced theory that are available a tenth or probably 100 of different piece of software to solve this particular density functional theory problem, and this generates enormous amount of data. So the idea now is to try to use this data, to harvest this data in machine learning. And the idea is then to combine these two very advanced theory into hopefully what can be a new theory that can get the best of both of them. And the idea essentially, there are a lot of problems to construct this link. First of all, we need to find out a very convenient way to represent the quantities that are relevant to density functional theory in a way which is amenable to machine learning. We are going to find, but then if this is possible, we're going to be able probably to speed up enormously the calculation in density functional theory. We're going to probably be able to access new quantity not available in standard electronic structure theory, and hopefully we will be able to construct a numerically exact function, so we will be able to solve exactly without an approximation the density functional theory problem. So this year I'm going to give project along those lines, and if you have any interest or if you just want to hear a little bit more, just please send me an email and we can organize a Zoom call or whatever can be done these days. Thank you and enjoy the rest of the day.
Hello and welcome to this presentation of the PhD opportunities within the Trinity Ultramicroscopy group under the supervision of Professor Lewis Jones and myself, Jonathan Peters. Our group's research is based around developing the state-of-the-art in electron microscopy, pushing the current capabilities through designing the next generation of hardware or by extracting new data from existing technology. We are really pushing the limits of precision, speed and sensitivity that's required for groundbreaking materials development. We are based in the Advanced Microscopy Laboratory just down the road from the main Trinity campus, where we have dedicated microscopy space with excellent facilities and support, from sample preparation to dedicated staff. One of our main focuses is scanning transmission electron microscopy, or STEM. The foundation of this is that we accelerate a beam of electrons close to the speed of light and into a single point, as small as a few tens of picometers across. We scan this beam across whatever sample we are investigating and collect a range of signals. At its simplest, we use an annular detector, which detects a signal when the electron beam scatters from an atom, or no signal when the beam passes straight through the material. This allows us to image materials all the way down to the atomic resolution, where, for example, we can now see the atoms in a silicon sample. We can even see atoms separated by only 136 picometers. One of the beautiful aspects of this technique is the ability to collect multiple signals simultaneously, such as spectroscopy from X-rays or electron energy loss, giving elemental and bonding information. Because of the power of electron microscopy, it has been fundamental in many aspects of modern materials research, particularly nanotechnology. Advancing these capabilities is where we come in. However, there are two main obstacles we face. First is the cost of the latest equipment. We can easily throw hundreds of thousands, even millions of euro at the problem, but instead we want to be clever and develop ingenious, affordable solutions that will extract the most out of our existing hardware. The second aspect is that our high-speed, high-intensity electron beam can easily damage the material we want to examine, particularly things like organic materials, light materials, such as those used in batteries. In order to look at these materials, we need to use our electron dose efficiently. Some areas we are actively developing include designing better magnetic lenses, electron emitters, or improving electron detection techniques through detector geometry and single electron counting. So this is where the new PhD projects come in. We are looking for students to fill two roles. The first is the application of state-of-the-art microscopy to do really new and exciting materials research. This will involve pushing the limits of our current capabilities to make measurements that were previously thought impossible, whether that be applied to semiconductors, ferroelectrics, 2D materials, or others. We have a range of collaborators from within Trinity, but also internationally to work with. The second project is for a data scientist to extract the maximum information out of the datasets that we can collect. We now have the capability to collect increasingly large datasets, from conventional 2D images to 3D spectroscopic images, and sometimes even 4 or 5 dimensional datasets. Whilst this data contains much more information, it also requires more advanced processing techniques. Here you can see a few examples, such as using principal component analysis to separate spectroscopic data into signals from different elements, scan distortion correction to achieve the maximum spatial precision from a time series of images, and compressed sensing that is used to reconstruct a full image from undersampled data. As well as new developments, there is also scope to improve existing analysis by making it faster, with the ultimate goal of running it real time as the data is collected, and also making the analysis robust with less human intervention required. This will involve the application and development of modern computer techniques such as. Another area we can improve upon is the simulation of our microscopes. Whilst we would love to say our microscopes are perfect, in reality there are always some imperfections to deal with. For example, our lens systems have hysteresis, and our current method of correcting this is just to wait for the lenses to relax. This is unsophisticated and introduces a massive amount of unnecessary electron dose to the sample. If we can accurately model this hysteresis, we can start developing methods to eliminate or compensate for it. We also need to start accurately modeling things like the energy spread from our electron sources, scan distortion for imaging, and improving simulation of electron to material interactions for things like thermal diffuse scattering. This work will really help guide the development of the whole group's research. So I do hope you have found this presentation useful. Please do get in touch if you're at all interested and we can discuss the projects. Thank you.
Okay, so David McCluskey is my name. I'm the Usher Assistant Professor for the Science of Energy and Energy Systems at Trinity College Dublin, and I run what I call the Nanothermal Research Group out of the School of Physics. This is me. This is a representation of my research group from about this time last year. A few new people on board now. So the areas of research that we are interested in, I would broadly say, are light and heat, and in particular where these two phenomena overlap. So some examples of projects that we're currently funded on are solar photovoltaics and solar thermal heating, where we are looking particularly at the performance of solar PV at high temperatures, and we're coming up with ways for reducing that temperature, and we've shown that we can increase the energy output from solar PV significantly by doing this. So this is currently funded under an SFI project, which is based at spinning out a company for a commercial application. Other things that we're interested in are at smaller scale. So we do a lot of ultra-fast optics with 2D materials. We do plasmonics. We do laser devices with integrated cooling, microfluidic channels and evaporation and stuff like this. And we're currently funded to look at ultra-fast modulators and display technology. Okay, so the first project that I've kind of outlined that I'd like some help with, somebody to do some work on, is related to looking at solar PV performance, particularly at high latitudes. So the price of solar has come down so much now that the people in countries that previously wouldn't have considered it economical are now considering it. So the efficiency of solar panels is anywhere between 15 and 20% depending on the technology you're using, and is roughly independent of irradiance, until when you get down to very low irradiances, it starts to fall off dramatically. And by low irradiance, I mean less than 200 watts per meter squared. Now, if you look at a histogram of available weather irradiance in Ireland, it turns out that for 60% of the time, we are in this region of low irradiance. Now, there are a few tricks that you can do to improve how solar panels perform in this region, and this is what this the gist of this PhD would be. We'll be working both on like a cell level where we put on nanoscale coatings to improve the absorption, but also on a panel level where we change the reflectivity of the glass surface. So that's project 1. Project 2 is related to solar thermal heating, in particular flat plate solar thermal. We're trying to improve its efficiency close to the tube-based one. And this is very important, I think, for decarbonising our energy system in Ireland, because if you look at the sources of energy going into space heating and water heating, you can see that it's almost predominantly done using fossil fuels such as oil, solid fuels, gas, and very little electricity or renewable penetration into heating your house and your water. Whereas solar thermal is a very effective way to do this, and by bringing the cost of this technology down, we're trying to increase its efficiency and increase the efficiency of transferring this heat into the house. Some concepts we're looking at reducing convective heat losses in these plates, and we're looking at designing radiators which work better at lower temperatures, which heat pumps and these kind of solar thermal devices work at. Okay, so if you're interested in looking at the world, finding a problem, coming up with a concept of how to improve or fix that technology, designing it using simulation software, and then actually fabricating it using various nanoscale or macroscale fabrication processes, then testing it in a lab and then testing it outdoors, then this is the kind of group or project for you, because this is what we're interested in. So if you're interested in either of these projects, or if you want to propose a similar type of project to us, please send your CV and a short cover letter explaining your interest to my email address before Friday the 2nd of October. These projects do take a little bit of time. You're going to have to write the majority of it yourself. I'll give you some input, so do contact me as soon as possible.
Hello everyone, this is John Donegan. I'm the Professor of Physics and Applications of Light in Trinity College, and I'm going to outline a project I'm suggesting for the IRC application. So it's termed soliton spectroscopy and dynamics in aluminum nitride and lithium niobate microresonators. So a soliton is a very particular individual type of wave that maintains its shape even if it propagates in time or in space. And solitons are caused when there is a cancellation of nonlinear and dispersive effects. Nonlinear optical effects generally occur at high optical powers, so again you need structures in which you can generate these high optical powers, generate the nonlinear effects, and then have them cancelled by the dispersive effects in the medium. So we do that in a system of a microresonator, as shown here. This is the case of an aluminum nitride ring resonator. The light enters into this waveguide as here, and then is coupled into the ring. Now this is the region here where you can see the coupling very clearly between the two of them. This is the input waveguide, and then we get coupling across into the ring resonator. And the light then can traverse round the ring many times as it does so, and eventually some of it also exits and leaves the waveguide again on the output side. So if we now look at the transmission of light through the system, this is what we find. So again, we are measuring in this wavelength range. This is in the near infrared, close to the region where optical fiber has its lowest loss. At a low power, optical power of 40 microwatts, this is what we see. We see a series of dips, and this corresponds to the positions where light is coupled effectively into the ring resonator. In other cases, light is not coupled here very strongly indeed in this situation. So these resonances are determined by whatever material and geometry that are there, but effectively where an integral number of the wavelengths fit into the ring radius, you get these transmission dips. Now, if you increase the power from these into the ring resonators, then on the output side, suddenly, instead of dips, you actually see emission. Here's a series of lines from this system, and again, a series of lines that are equally spaced is actually called a comb, remind you of a hair comb. And all sorts of different arrangements can be generated. This one is called a chaotic one, where the lines are not so equally spaced. And then at the top here, we have a very beautiful representation of what's termed a soliton crystal. Well, you can see again, a large number of lines are generated, and they are roughly 5 of what's called these free spectral range apart. An even more extraordinary and beautiful creation is the soliton So this extraordinary spectrum, as shown here, is a series of hundreds of individual lines which are generated from that ring resonator. So let me explain quickly what's happening. Here's the pump wavelength coming in our waveguide. Generates the resonances, all these comb lines, as from the previous arrangement that was there. And when we balance carefully the dispersive and the nonlinear effects, then we generate what's called a soliton. And in this situation, it generates a very short pulse of light on the order here of about 66 femtoseconds. Imagine that extraordinary behavior from such a tiny, tiny resonator. A particular aspect of solitons is that they are a quiet or a low noise state. And in fact, if you look at a photodiode, which takes the optical power from all of this, you can barely distinguish what you see from the photodiode when there's no light on it than when all of these lines are present on it, indicating again this very low noise state. In fact, in this system you can generate not just infrared light, this is all infrared frequencies, but in this image here you can actually generate green light, and there's red light generated, not quite so strong to your eye, from this. So these harmonic generation effects are also present in the system. So again, extraordinary behavior is possible from just a simple ring resonator. So for the IRC application, solitons themselves are key in the development of a new optical frequency reference, a reference that has an uncertainty in just 1 part in 10 to the minus 15, quite extraordinary level of precision for the frequency of the light. We're going to do this by developing solitons in aluminum nitride resonators and lithium niobate. That's a different material. Particularly, you can electrically tune it, and that's why it's interesting. So to really make this happen, we have to use important fabrication techniques, including electron beam lithography. The system is modeled by the nonlinear Schrödinger equation, and again, that's an important part of what has to be done here, is the modeling and the experimental work working together. And in turn, we will also use laser systems that my group has developed over many years in the hope of generating again all of these lines from the UV to the visible to the near infrared. Now, as you know, I probably haven't explained, the IRC is a very competitive application process, so students must have a first honours result from their third year. And if you want to talk about this more, please contact me as follows, jdunnigan@tcd.ie. And thank you very much indeed for your time.
Hi, welcome to everyone back to Trinity for the final year. So many of you remember me from first year. My name is Louise Bradley and I lead the nanophotonics group here in Trinity. I want to tell you a bit about firstly the group and then the specific project which I would like to apply to the IRC for. So my group specialises in the generation, manipulation and detection of light on the nanoscale. We're funded by lots of different funding agencies, including Science Foundation Ireland, the Irish Research Council. We also have Marie Curie funded postdocs in the group, and we have PhD positions funded by Amber and by IPIC, which is the Photonics Centre in Cork, and we also have received funding from Tyndall, which is a national access programme. So this is the current group. There are 3 postdocs and 7 postgrad students in the group at the moment. The project that I want to tell you a bit about today is based on novel optical sensors with 3D printed responsive polymers. This project will be in collaboration with Professor Larissa Florea from the School of Chemistry. So Larissa specialises in the development of the responsive polymers, and they can be printed into any type of 3D structure using the nanoscribe tool, which is down in the Advanced Manufacturing Laboratory of Pearse Street, and it's based on the process of 2-photon polymerization. So what we want to do in this project is to take the materials which have been developed and to understand and quantify the changes in the structures which we make using the nanoscribe, and also to understand the changes in the refractive index when these responsive materials are exposed to different kinds of stimuli, whether those stimuli are liquid or gas. And then based on this knowledge, we want to be able to design and to fabricate and ultimately to test structures which have been optimized for a range of sensing applications. So I'm going to give you an example. So here you can see a checkerboard type structure. So the micrographs there taken with the scanning electron microscope show that we have one structure which has got a period of over a micron and the other one which has a period of about 500 nanometers. So when we look at the different structures in the transmission spectroscopy, you can see that they correspond to very different colors. Now, if we expose this structure to IPA vapor in a closed cuvette and we monitor what happens as a function of time, we can see that there is a distinct colour change arising as the IPA becomes more concentrated in its gaseous form. So if you look across the top, we can see that the top square goes from a greeny yellow colour to a more progressively blue colour, then to a reddish orange colour, and then it starts to fade towards a lighter bluish colour. And across the bottom also we can see distinctive changes in colour going from green to a very dark blue to a reddish orange and back then to a light blue. This is completely reversible and the response will be different for different kinds of gases and liquids. So for example, here you can see the spectra that we take in transmission, and we can monitor these spectral changes as a function of time. So what we want to do in the project is to explore a range of possible polymers, and we have free design of our structure. So we want to quantify, design, optimize and test for different applications, considering both gases and liquids. We'll do a series of measurements which include dynamic spectral measurements, angle result measurements, as well as using a range of techniques to probe the structural changes within our materials. And from this we hope to develop a series of structures which will be able to be used as colour monitors or even spectral monitors with a wide dynamic range. There are other funded positions available in the group as well. They're on the topic of plasmonics. If you're interested in finding out more about those, please contact me directly. Thank you for your attention.
So, hi everyone. In this short talk, I'm just going to describe the PhD project I'm offering this year. So the broad title is The Ever-Changing Universe, Exploding Stars and Catastrophic Collisions. And so my research focuses on understanding some of the most energetic explosions in the universe. So we do this by looking at supernovae. So these are the explosions of stars at the ends of their lives. And these can massively outshine their host galaxies, as is shown here. So these are very energetic explosions. And then I'm also interested in are actively involved in the new field of the follow-up of gravitational wave detections. So this involves the collisions of neutron stars that now with the LIGO Virgo experiment and then electromagnetic follow-up that we can see and hear. So some of the big questions that we want to answer are, how do normal type 1a supernovae explode? Can we explain the extremes of stellar explosions? There are a lot of weird things out there. How do they explode? And this is really testing the boundaries of explosion models. And then what is the diversity of neutron star mergers? So starting with type 1a supernovae, so these are the explosions of small dense stars called white dwarfs at the end of their lives. They're the main producers of iron in the universe. So any iron on Earth was most likely produced in a type 1a supernova explosion. They're also critical in the discovery of dark energy, so in understanding the cosmology of our universe. And so we now know from studies of supernovae and the cosmic microwave background that dark energy makes up approximately 68% of the mass energy of the universe. Dark matter, about 27%, and then the ordinary matter that we see around us, people, the Earth, galaxies, this only makes up 5%. So type 1a supernovae are essential for understanding cosmology and the makeup of the universe, but the key problem we have is that we don't actually understand how they blow up. We just use empirical relations to use them for cosmology. We want to be able to do better than this. So there are two leading mechanisms for how a type 1a supernova explodes. One, as shown here, is the case where you have a non-degenerate companion star, so some kind of main sequence star or red giant that is onto which a white dwarf is accreting matter. And this causes it to approach the Chandrasekhar mass limit, which triggers a runaway thermonuclear explosion. And this completely destroys the star. In the other case, you can have the merger in a number of different ways of two white dwarfs. So in this case, you can see in the video here, two white dwarfs merge, and this can also produce an explosion that for some models is consistent with a type 1a supernova. So one of the key questions we want to try and answer is which of these scenarios is producing type 1a supernovae, and it looks like it potentially could be both. The other key question, as I said, that I'm interested in is understanding neutron star mergers. And the key astrophysical question that we can answer with this is where are our process elements produced? So these are elements heavier than iron in the periodic table, and it's a long-standing question in astrophysics whether they're produced in quark collapse supernovae, as you can see on the left, or in neutron star mergers, as you can see in the video on the right. It's only been possible with the recent detection 3 years ago of 2017 GFO that was detected in gravitational waves, and then subsequently in electromagnetic observations. And from this, we were able to predict or show that it was more than likely that this was producing gold. So you can see here the light R process and the heavy R process elements, and you can see where gold sits in atomic mass number. And so, yeah, the key question we want to answer is try and find more of these in this first kilonova event. And then we also ask the question, the questions that I've been saying about what stellar systems produce type 1a supernovae, is all gold made in neutron star collisions. So if you're interested in any of these topics, please get in touch with me. You can send me an email. It's kate.maguire@tcd.ie, or you can find my information on the physics web pages. I look forward to hearing from you.
Okay, so hi everyone. My name is Neil Gibson. I am an astronomer here at Trinity, and I'm going to tell you about a couple of PhD projects we have in the field of exoplanet atmospheres. As you probably know, thousands of exoplanets have been discovered since the 90s. So exoplanets are just planets that orbit stars other than our sun. And this is just a plot of the planet mass versus orbital separation, just a way to represent the exoplanet population. And I've overplotted the position of Saturn, Jupiter, and Earth, and so on here. And one of the key things is that the planets are much, much more diverse than what we see in our own solar system. The problem is we don't really know that much about them beyond simple physical measurements like their masses, radii, orbital properties, and so on. So the goal of my work is really to find ways of understanding these planets in much more detail. And to do this, we need to get spectroscopy of their atmospheres. So the key to doing all this is something called planetary transits. So many of you will know a planetary transit is just when a planet passes in front of its host star. And if you measure the brightness of the star as a function of time, you'll see this characteristic dip. And it's just because the planet blocks a certain portion of the light from the star. And we can use this to not only detect the planet, but also to measure the mass of the planet as well. And transits don't just occur in exoplanet systems, they also occur in our own solar system. And this is just a really beautiful picture of the sun. You can see sunspots and so on, and you can see Venus transiting the sun. And what I want to bring to your attention is that if you zoom in on Venus during one of these transits, you actually see this very thin annulus of light. And essentially this is light that filters through the upper atmosphere of the planet. And if we can get access to this, the light that filters through the atmosphere, we can learn a lot about the atmosphere itself. And this is a technique called transmission spectroscopy. It works for exoplanets as well as solar system objects. And if we can get access to this, we can learn lots of cool things like the composition of the planet, the chemistry, scattering properties, temperature structure, and so on, things about dynamics. And long term, we're hoping to use these techniques to find things like biomarkers. So in other words, signs of life. So maybe oxygen in an Earth-like planet, for example. So there are two primary techniques to do this. One is just to take a series of transit observations. So these are just, again, the brightness of a star as a function of time. We do this at multiple wavelengths, and we measure the transit depth as a function of wavelength, and we get the effective radius of the planet that we can just convert directly into a spectrum. So I'll not go into a lot of detail here, but we can use this to directly observe the spectrum and then learn some information about the planet. So in this case, we get some sort of scattering signature, which indicates clouds, hazes, or so on in the planet. So another thing we can do is to observe high resolution spectroscopic observations. So again, I'm not going to go into a lot of detail, but similar to the radial velocity method that we use to detect exoplanets, so we measure the Doppler shift of the star as it orbits the common center of mass, we can use the much larger Doppler shift of the planet to actually disentangle the planet spectrum from the stellar spectrum. And we do some data processing, and we end up with a plot like this. So this is essentially you're separating your signal in velocity space. So this is the velocity amplitude of the planet versus the velocity of the whole system. If you see a spot in the right position, you can use this to detect atmospheric features. And this is what we're hoping to do in the future, to detect things like, as I say, oxygen and Earth-like planets. So what is the project itself? It's essentially to investigate and learn these two techniques. So essentially to observe time series spectra of star-planet systems. And we use some of the world's most advanced telescopes, such as the Very Large Telescope at Paranal, which you may have an opportunity to visit at some point, and also things like the Hubble Space Telescope. And we take these observations, and then most of our time is spent trying to disentangle these tiny signals from the exoplanet atmosphere from the host stars. So we use a lot of sort of advanced statistical techniques to do this, to try and disentangle these signals. Once we've done this, we then model planetary atmospheres in order to interpret the data. And of course, we want to prepare for things that are coming in the future. So there's a couple of really interesting facilities coming online in the next few years, which are really well timed for these projects. One is the European ELT, which is going to be the world's biggest telescope. It's going to have a 36-meter diameter, and it's going to be amazing for starting to look at terrestrial planet atmospheres. We also have the James Webb Space Telescope, which is hopefully going to launch next year, and it's hopefully going to do some great things too. So if you're interested in astrophysical observations, atmospheric physics, exoplanet detection, characterization, stats, and machine learning, then give me a shout and I'll tell you some more about the project. So thanks a lot.
Hi everybody, my name is David O'Regan, and I'm going to speak to you for a few minutes about the work that we're doing at present in the area of quantum materials theory, and a project that I think would be quite interesting to develop an IRC proposal on building certain quantum mechanical exact conditions into the simulation of materials for renewable energy processes. So these could be solar cell materials, for example. They could be battery materials, or they could be materials for catalysis for conversion of CO2 into liquid fuel. Okay, so we're actually pretty diverse in my group in our interests, and we can develop projects on different types of topics, all the way from quite theoretical up to really an applied project in collaboration with experimentalists. So to discuss the types of options that we have in materials theory in general, just pop me an email, it's no problem. Okay, we're a group of, myself, 3 PhD students at present, one postdoc being hired at present, and one up the sleeve. So we're a mid-sized group. And broadly speaking, where our interests lie is in broadening the scope and the relevance of quantum mechanical simulation of materials. And this involves sometimes developing new pen and paper theory to make the simulations more accurate. Depending on the student's interest, we can do quite a lot of software development. We try and make that modular and user-friendly. And then, some students prefer to just take the software off the shelf and really get to grips with the physical problem. So we do respond quite a lot really to real-world requirements and needs. We interact with industry. and experimental colleagues quite a lot. And this takes us really right across the material world. So we've looked at oxides in the past. So these are the types used in certain types of solar cells, even semiconductor whole devices. So these are single photon emitting quantum dots of relevance to quantum computing, even up to very complicated systems like metalloproteins in the human body. This is myoglobin, so we're into quantum biology there. And we looked at nanoscale properties. These are mechanical properties of different metals in adhesion at the nanoscale. We look at photonics and plasmonics, so this indicates the response of different metal alloys to laser light. And we also do even classical modeling. So this is some modeling we've done a couple of years ago to try and predict really the size and morphology that different types of two-dimensional material like to adopt. So we're pretty diverse in our interests, really, and we're able to incorporate the needs and interests of different types of students. But broadly speaking, we're doing quantum mechanics, and we're using a formalism of quantum mechanics known as density functional theory. And I like to think of density functional theory as the biggest thing that no one ever heard of. So it's one of the most influential ideas in science, I think, in the last 100 years, but it somehow doesn't make it into our undergraduate courses. This is a bibliometric study from nearly 10 years ago, showing that at that time, something like 18 out of the top 22 physics papers or papers in American Physical Society journals were about density functional theory, and how to make this quantum mechanical theory into a practical method for simulating materials. The runners-up, the other papers, are little old things like the theory of superconductivity, the BCS theory. Now, I jest a little bit. I mean, density functional theory is if you want, a necessary evil in some ways. It's the only practical way that you can use quantum mechanics to explain and predict the properties of real-world materials on moderately sized computers, the sorts of computers that most research groups have available. So it's very, very influential. But actually, for real quantum materials, for materials that are really of most interest for carbon sequestration, for photovoltaics, for very high performance magnets, these are materials. There's quantum materials for which quantum mechanics is responsible for the key properties of interest. Actually, it's the multi-reference, if you like, Schrodinger's cat effects that makes density functional theory perform very poorly, and that's where we come in my research group. So if we look at manganese monoxide, which is a very challenging system, it's not unlike the pairing materials for high temperature, certain high temperature superconductors. Standard density functional theory gives you absolute garbage, basically, for the band gap. So it gives you a large spread of results depending on which version of density functional theory you use, and they all underestimate the band gap with respect to the experimental band gap, which is down here around 4 electron volts. You can use a very expensive version of density functional theory. You push up the average value, but you still have a big spread. And you can even go beyond density functional theory to Green's function-based methods that are getting very, very expensive, and still you do quite a poor job. So this is where we come in my research group. What we've been developing for the last few years are these methods to, on a case-by-case basis, measure the error in density functional theory. We measure the strength of its breach of certain known quantum mechanical exact conditions, and by hand, really with sort of cheeky pen and paper tricks and code hacks, we put the right physics back into density functional theory. I mean, there's a lot of technical detail under the bonnet, and it's actually quite a rigorous thing, but this is where we are in practice. We can get just from this system, and I have many other examples like this. I just show you one. Good agreement with experiment. So this is an area that I think is taking off, and we have been looking at kind of very canonical test cases that are hard for density functional theory up to now. But I really want to push this forward now into the realm of materials that are cutting edge, and particularly I'd like to take this theory, which is developed to be energy efficient on supercomputers, and actually use the theory to try and discover, explain, and develop new materials for energy applications. Okay, so the idea is you have a self-correcting density functional theory that's self-contained, transferable from one material to another, accurate, efficient, easy for people to use, and really to disseminate this methodology in as many DFT codes as we can reach or we see relevant, and to apply these and to make interface with the experiment where it's most relevant in the energy realm. So we could look at, for example, phase diagrams of high performance battery materials. There are certain new categories of photovoltaic materials and transparent conducting oxides for solar cell applications, or there are things like zeolites for capturing and catalyzing toxic gases or gases like carbon dioxide. I mean, I'd be very interested in actually combining some of the methodology that we've been developing in a hybrid theory experiment project, for example. But there are different types of projects that we can develop and really tailor to the individual interest of the student. So some students would just prefer the theory. They actually like doing applied quantum mechanics, pen and paper exercises. Some students love software engineering, so they love coding, they love high performance software. And some students just want to become the expert on a particular class of material and drive the physics and the chemical physics forward there. And some people find it very, very stimulating to interact and even participate in experimental work. So I think there's a full range there that we could think of developing an IRC project on, and I would be willing, I think, to support one or two applicants this year. Much more than that, and I think one spreads a little thin. So I'm very, very happy to be contacted. You have my email address here, david.o.regan@tcd, and I look forward to hearing from you. Thank you very much.
Hello, I'm Michael Coey, and this short video will let you see some of the things that are going on in our magnetism and spin electronics group. As you can see from last year's photo, which was taken pre-COVID, we're one of the bigger research groups in physics, and every year we take on 2 or 3 new PhD students. Magnetism is a really exciting subject. It underpins the information and big data revolutions, and new things are being discovered all the time. There's been a Nobel Prize for magnetism roughly once every 10 years. Our labs are split between SNIAMS and CRAN, and we'll have a peep into each one. At the end, Plamen will tell you about the new PhD topics. But here we are in SNIAMS, and Lucy will take over for this part of the tour.
Hi, I'm Lucy, a second-year PhD student in the group, and I'm just going to show you around our lab in the SNIAM. So in this lab, we make materials in bulk and thin film form. Here you can see Hassam making alloys using the arc melter. So he's melting the metals by means of an electric arc to form alloys with a particular composition. But we can also prepare thin films in the SNIAM, and we do this using pulsed laser deposition. With this technique, we strike a target with a laser which vaporizes the target material and forms a plasma plume. The material then deposits onto a substrate, resulting in the growth of a thin film. So at the moment, I'm using this to grow metal oxide films. After preparing our samples, we need to magnetically characterize them, and the SNIAM is the home of our very own SQUID magnetometer. So SQUID is a strange name, but it stands for Superconducting Quantum Interference Device, and it allows us to apply a magnetic field to a sample and measure the resulting magnetic moment. We can scan fields of up to 5 Tesla. We can also vary the temperature from 4 Kelvin up to about 400 Kelvin. But if we want to measure the magnetization at higher temperatures, we need to use our VSM, or vibrating sample magnetometer, which is being fixed up at the minute. So Zetian, another PhD student in our group, is working on this. Here you can see him designing some parts on SolidWorks, which he then printed using our very own 3D printer. It's extremely convenient to be able to print anything you need, really. People in our group have been using it frequently since we got it in the last year. There are also members of our group studying the effects of magnetic fields on liquids. So Sruti here is using some new equipment to measure sessile and pendant drops in order to determine the surface tension of different liquid samples. So now I'll hand you back to Mike, who will take you through CRAN for a little tour of what we can do in our lab over there.
Now we move over to CRAN, where we have state-of-the-art facilities for nanoscience research. It's here we do most of our thin film growth and patterning in the clean room to make devices, and we also make all of our electrical and optical measurements over here. Most samples we need are thin films or complex thin film stacks. This one is a tunnel junction sensor. And we're really lucky to have the new €3 million TEDI facility where we can make near-perfect devices by sputtering in ultra-high vacuum. The tool also includes chambers for in-situ study of the films just after we produce them. They must be thoroughly characterized by X-ray diffraction, microscopy to see if there are any magnetic domains, and then by squid magnetometry over in SNIAMs. Next, we pattern them lithographically into the shapes we need for detailed electrical measurements, which we make with different directions of field and current, and also different temperatures. Sometimes we need to see harmonic response to AC excitation. Here, Simone and Zhejiang are making measurements on a new 10 nanometer thick amorphous film of dysprosium cobalt at temperatures from 5 to 300 K in a magnetic field of up to 5 Tesla. It's produced in the bore of the big green superconducting magnet, where no liquid helium is needed. But some of our most original data comes from ultra-fast optical measurements in the photonics lab, and Chandrima will now give you a little tour.
Welcome to the Photonics Laboratory in CRAN. This lab is dedicated to several state-of-the-art ultra-fast high-energy laser systems. Using optical tools, these laser pulses are fired on the sample under study. As we are interested in magnetic systems, our main area of research is ultra-fast non-equilibrium magnetization dynamics, which are as fast as sub-picosecond in time scale.
And now Plamen will briefly run through some proposed project ideas for any new PhD students that want to join our magnetism family.
Hello, I'm Plamen Stamanov, and I'd like to present to you 3 selected topics that are available for you this year. The first one has to do with creating a magnetic neural network, the weights of the synapses of which we can adjust rather rapidly and effectively infinite number of times. The second has to do with applying amorphous ferromagnetic materials into relatively complicated magnetic stacks which aim to achieve non-volatile logic functionality on chip. The third has to do with trying to revolutionize how we switch optical data transfer and modern optic fiber networks by magnetic means. Last, I'll just want to leave you with a couple of ideas for titles for projects that we could also support in the course of the next few months. Below you can see the contact emails.
Hello, welcome to my talk for an IRC postgrad project. So the topic in general is light at night and light pollution. So why is light at night important? Well, it tracks human occupation and its activity. So the image at the right, for instance, shows the 2 Koreas. North Korea, quite dark. South Korea, relatively bright. A lot more activity. Look at the sea as well. There's light from squid fishing boats with the use to attract the squid. So where humans are located is traced in the lights, and we can use this to track lights and activity night on night. But the other side of this is that the light we see when we look down from space also indicates an energy loss. And the energy being used for lighting and light pollution is increasing at 2% annually. It's driven by our 24/7 culture and the increases in both population, the growth of light into the into the environment, and also development in the economy. So all of this has an obvious energy cost, but also monetary and environmental cost, and at high levels can actually affect human health. The image to the right, in the town of Bath in the UK, images taken several decades apart, we can see quite a dark area in the top image, something we'd regard as quite dark by modern standards. In the bottom, a lot more light. So although light can be a lot more controlled nowadays, we're using it a lot more frequently. Buildings are illuminated. We can even see light shooting off into space in the building on the right. The bottom picture shows an image taken from Killiney Hill looking back over the city, Comet Neowise, recently, and you can see the amount of light acts to damage the astronomical environment. So all of this requires that we quantify the light emitted and to understand its origin, how it propagates out into space, but also how it propagates out more widely into surrounding countryside, and all the costs associated with this. And if we come up with a quantifiable prediction, we can use this for modeling, forward modeling, and predicting where the likely changes in light is going to occur, what we can do about it, and that can inform policy and planning. In the Republic, the image at the top right shows areas where light has been increasing from 1995 to 2010, and we can see it's increased in the red color. Blue color indicates decrease, and white indicates no change. So the white is basically areas which can't be built on. The graph shows the measurements taken from space. We see a 10 times faster growth in the Republic, and this increase in light then means that we're having a much more big impact on the environment. And the bottom picture shows an image taken from Wales, 120 kilometers away. In terms of the public aspects, we've got nearly 500,000 lights, quite a large amount of lighting, but there's also a commercial component, as indicated in the reaction to the Celtic tiger, the growth, and also new lighting, new more efficient lighting and cheaper to use can actually lead to an increase in light because it's used more frequently. So the image at the bottom shows the change in the center of Milan as white lighting from LEDs were introduced. So we need to quantify these developments and model them. The image here we show Dublin taken from the space station. We can see the different types of light. Blue is new LED lighting. We can compare that with the public lighting and come up with a model for see, can we calibrate that? Can we predict what the light should be emitted and what we detect from space? And over nearly 2 orders of magnitude, that's what I see in the sample areas. This work done by a final year project student and myself. So we can map to these local sites and develop a calibration and then compare that with the ground energy use and derive the corrections. But we need to actually understand obscuration and scattering and effects as well. Luckily for Dublin, we have a very good LiDAR model, a laser altimeter model. We can actually model the locations of buildings, their heights, and so on. And then we can use the model then to predict how much light is going out into the environment. We can quantify these in different directions, different types of light, different colors of light. Trinity is one of the few areas working in this field. It's getting a bit of a reputation internationally. We have high resolution satellite imagery. We can look at the effect, important topic now, the effect of the economy in light, COVID-19 effects, correlation with activity, and as you can read there, land use, commercial, retail. We want to strip that off and understand these various components. So we can use radiative transfer models to understand and compare our results with international cities, as well as supply recommendations for the government at different levels. If you're interested, please contact me at brian.espy@tcd.ie. Thank you. Thank you.
So I'm Paul Eastham, and I do, as you can see from these slides, theory of quantum light and matter. So I guess the question is why you might want to join my group. Well, I think the main reason is you want to do theory. TP students, as far as I'm concerned, it's something you can do irrespective of your speciality. At this stage, I mean, I have a physics degree. So, you know, what is the qualification? Well, I think the qualification for being a theorist is, do you want to make theories? That's what we do. And in my case, those theories are mostly equations, like those of quantum field theory, that we study with pencil and paper methods, and sometimes computational methods. So if that's the sort of work that appeals to you, making theories of your own, you